Hello, my group will be presenting our final semester project, which is the feasibility analysis of aircraft landing gear. So to begin, a little bit of background, landing gear is one of the most important systems in an aircraft. It provides a stable platform for taxiing and to build enough speed during takeoff, and it must be able to sustain the weight of the aircraft during landing and any other loads that it experiences during landing. The purpose of this project is to design a functioning front landing module and perform SolidWorks simulations to optimize the longevity, strength, and cost of all parts in the landing module. Our idea behind this is that if we optimize longevity and strength, so those are going to be our main two parameters to increase. If we increase those, we'll be decreasing our costs very much so. The reason for that is because if we increase longevity and strength, even if we have more upfront costs, we're going to decrease our maintenance costs over time because we are going to have less maintenance performed on the aircraft because we're going to have parts that last longer. In the weight and size are also considered as to not exceed standard values. And one important note to make about landing gear is that landing gear is typically the last major system that is designed in an aircraft. The reason for that is because there are multiple different factors that play into what the specifications of the landing gear has to be. Items such as the fuselage, wing, and tail are built first. The reason for that is because you need enough clearance in order for the wings and the tail to not encounter the runway, especially during takeoff. One example of this can be seen right here. So this plane has wheels that are not either long enough nor in the right position. Therefore, during takeoff, whenever it reaches its takeoff angle of about 10 degrees for most aircraft, its tail drags that ground. Now, you want to design the landing gear so that it has enough height and it's in the proper placement that you have a safe clearance between the ground and your tail whenever you take off. This is one of the most important parts of designing landing gear, and that's why landing gear can't just go on any aircraft. And for the purposes of this project, we didn't design a fuselage or wings or tail. So we just kind of built a generic landing gear that will fit any small to medium-sized airliner.
All right, now we're going to move into our project's objectives. So first and foremost, we wanted to create functioning landing gear that is much stronger than landing gear used today. Landing gear that's going to survive greater stresses, that's going to be able to survive a lot longer and lower long-term maintenance costs. We also wanted to take our design and put it to the test in stress and fatigue analysis to prove that what we're saying is actually happening. And we're making our landing gear stronger by utilizing different materials for different parts of our assembly. And then finally, we wanted to develop project management skills. So we wanted to take stuff that we learned from this project and be able to apply it to our maybe senior design project or future projects in general. And I'll move into how our design differs from the market landing gear. So the majority of all market landing gear is made of steel. That's the main material for the shafts and what's taking the force of the landings again and again and again. We are trying to replace that main shaft with carbon fiber, a material that is much stronger, it's much lighter, but it does cost a little bit more. But we're hoping that that increase in strength, increase in durability will lower the long-term cost of it. It won't need to be replaced as often. It won't need maintenance as often because it is that much stronger. And with that meme down there, you see Leonardo DiCaprio, don't gamble, think long-term. That's our idea for this project. We are creating landing gear that not only weighs less, but is also much stronger than the steel counterpart you see today. But that stronger landing gear will cost a little more up front, but it will survive longer and will lower long-term maintenance costs. And now to take over for literature review, moving on to Matt.
Okay, so upon research of the design of aircraft landing gear, we quickly learned that life cycle cost is a major consideration in the design process of aircraft landing gear, and that you need to strive to minimize that. Well, how do you minimize the life cycle cost of anything? Design optimization. In design optimization, you have an objective, in our case, minimizing the life cycle cost. And then you subject that objective to design constraints, in our case, the dimensions and the materials. Dimensions. Typically, the bigger something is, the more it's going to weigh. You don't want that in aircraft landing gear. It's going to be in an airplane. It needs to be light. And it can't take up too much space because you're trying to make the whole aircraft as small as possible to, again, keep it light. Materials, you want strong materials, again, that don't weigh too much. So you can't just have heavy materials everywhere. It's going to be strong, but it's going to weigh a ton. It's not going to work in an aircraft. Nose landing gear on aircraft, we learned, needs to support between 10 to 20% of the total weight of that aircraft. So this is because the way aircrafts are typically set up, the rear landing gear on aircraft supports the majority of that weight. You can lower the percentage of the aircraft weight that the nose landing gear needs to support by moving that nose landing gear further forward. Since we don't have an actual aircraft to model off of, we just chose to use this 10 to 20% range for finding the weight and the load that our landing gear needed to support. Safety. Safety is a high concern in landing gear design. It's an airplane. There's people going to be on this airplane. They need that landing gear to work correctly and be safe in order to land, because they don't want something catastrophic to happen. We learned during research that wheels are a way to increase the safety of landing gear in aircraft design. This is because the more wheels you add to the nose landing gear or any landing gear, you're adding to the contact area that you're distributing the load across with the ground. So you're distributing that load more evenly, and you don't have concentrated forces on one particular component. So the industry standard for smaller landing gears such as ours is 2 wheels. That's what we chose to use. There are 1-wheel design, but again, we wanted to maximize the safety of our nose landing gear for our aircraft, so we chose to use 2 wheels.
Hi, my name is Ben Stewart, and I'll be presenting our methodology section. So the first step for our project was to define our desired design outcomes. Our 2 main design outcomes were to maximize the longevity and reliability of the forward landing gear component for an aircraft, while also decreasing the overall costs associated with upfront expenses and maintenance. And we kind of weighed upfront costs versus maintenance costs when choosing materials. So jumping forward to that point, the next step for us was to choose our materials. So weighing kind of a cost to strength ratio, we settled on carbon fiber and steel as our 2 main materials for the full assembly. So one thing to note about carbon fiber versus steel is that carbon fiber is 5 times stronger than steel, while also weighing anywhere from 1/5 to 1/10 of steel. So for a weight to performance ratio, carbon fiber was, clearly outperforms steel in that respect. And when designing aircraft landing gear, weight to performance is a big thing to keep in mind. So after we had decided on our materials, our next step was to determine our approaching methods for achieving our design outcomes. So to do this, we chose to use SolidWorks finite element analysis. This would allow us to create a functioning model of our landing gear and then run numerous simulations on it to prove our design outcomes. So next we have functionality. We're going to show a quick video here that demonstrates the functionality of our design as it relates to the movement capabilities of the design. So we've got our design here in SolidWorks. And this first motion shows the landing gear actually retracting up into the fuselage of the aircraft and how that's done using a simple linkage system. And then second part of the video here kind of shows how the suspension would work on the system. As you can see there, the wheel moves up and down relative to the main body of the landing gear, just as the suspension would work in a practical application. So by designing our model in the way shown in the video, it allowed us to perform various types of analysis within SolidWorks. Some of these analysis include stress analysis, fatigue analysis, and optimization. And we'll get a little more into detail with those in the results that we got from running those analysis later on in the results section. So one last thing here for our kind of methodology section was our project schedule. So as you can see, starting here at February 10th and going all the way to April 24th, we have kind of all of our main project milestones laid out with specific dates. And by doing this, it kind of helped us stay on track and make sure that we were accomplishing all of our tasks throughout the course of the semester and that we weren't, crammed at the end to try to get everything done. So that being said, I will pass along to one of my colleagues to discuss the results. Thank you.
Now for the results. Our first outcome is a fully functioning model of our landing gear. Above, we have the system in the takeoff/landing state. This is where it's going to take on the full load of the plane. Below, we see that the landing gear is capable of retracting by using a simple link system. Our next outcome is stress analysis. On the left, you can see that the axle takes on the most stress due to the load of the plane and therefore is the most important in our design. On the right is the stress analysis for the load on the simple link system due to the weight of the assembly. Our next outcome is displacement analysis. You can see below that the tires undergo the most displacement. This is because the rubber tires are more malleable than the other parts and therefore are displaced further. Our next outcome is the S-N curve and subsequently the fatigue analysis. In order to perform fatigue analysis, we first need to look at the S-N curve. The S-N curve on the left will tell us if the part will fail due to cyclic loading. On the right, we see that our assembly is strong enough to endure the effects of cyclic loading. Finally, we wanted to reduce the cost of our most expensive parts. This includes the top and main supports. The optimization was set to minimize the stress, displacement, and volume of each part. As you can see below, our optimization was successful.
Okay, and in conclusion, the SOLIDWORKS simulations on the landing module showed a life cycle exceeding 1 million cycles and a maximum displacement of approximately 12 millimeters, which occurred in the tires of the assembly. Certain areas experience higher stress than others, so these are designed with stronger, more durable materials. We look for materials that had an especially high yield strength, that way they'd be longer lasting. Future work includes adding an AI system to communicate with the pitot and radar altimeter to automatically deploy or retract the landing gear. That way, whenever we get to a certain altitude off of takeoff, the landing gear would immediately retract, and whenever we get back down to a certain altitude, the landing gear would automatically deploy. And we also had the idea that during landing, whenever you're coming in, it would communicate with the pitot, so we would know the velocity of the plane, and a motor in the wheels could spin the wheels to match the velocity that the plane is moving at. This way, the tires would last longer, and we would just be decreasing our maintenance costs if we were to do that. Okay. And here are our references. Thank you all very much.